supposed to applaud. Come on. Yeah. Hi, everyone. Hi, everyone. Thanks for coming. My name is Matthew Rocklin. This is Mark Wiebe. We work for Continuum Analytics on a project called Blaze. Okay. So the context of this talk is that we all love NumPy and pandas. And I'm actually going to argue that our community would not exist without NumPy and pandas. These data structures are foundational, meaning that they sort of serve as the lingua franca between all of our different projects. SciPy produces NumPy arrays, which we send to scikit-learn, which we send to scikit-image, and these sort of centralized abstractions allow us all to communicate, all of our different work to communicate. Otherwise, we'd be figuring out all of these communication mechanisms. It'd be terrible. Recently, pandas showed up and did the exact same thing for more sort of tabular computations. Computations you might have otherwise done in SQL. So we're going to claim these are sort of foundational data structures. Also, they're foundational abstractions. Okay. But they have this one small issue. The way that they're built restricts them mostly to memory. It's sort of inconvenient to go outside of the memory of your machine to use them. In-memory computation, good for like 95% of your problems. The other 5%, not so much. Turns out the other 5% pay pretty well. So there's actually been lots of projects that have been working on making projects that are like NumPy and like pandas, but go outside of memory, either through streaming, or by out-of-core algorithms, or by distributed computing. So just to name a few, nthought, there's distarray, there's SciDB, the array database, Elemental, Petsy, and Trilinos, all for more sort of traditional high-performance computing. Bigus is around for meteorological data. Traditionally, Blaze has done some work in this. We're actually not going to talk about that. We'll talk about other things. But so lots of projects have tried to build NumPy-like systems that go outside the scope of NumPy. I want to sort of stress this, that each of these approaches is valid in a particular context. So you can't sort of say, oh, this one's better, this one's better. They're all valid. It depends on your problem. Okay. If you look at sort of the pandas side, or sort of the tabular side, there's systems like PyTables for out-of-core HDF5. The SQL Alchemy is a great Python project for interacting with SQL databases. I'm actually going to sort of push SQL. There's been a lot of anti-SQL or no-SQL movement. SQL is an awesome technology. It's a little bit slower than pandas, but it's still quite robust. There's the Hadoop file system world, things like Hadoop, top of that, Pig and Hive, Spark, Impala, sort of very active, very active space right now. The R community doesn't have a whole lot of interaction with, and maybe we should. So if you're dealing with sort of tabular computations, something to look at. And again, I want to claim that each of these approaches is valid in a particular context. So depending on your problem, one of these might be better or worse than the other. There's sort of no winner take all in this contest, I claim. Same exact thing for data projects. We'll talk about some of it later. Lots of different data formats. They're all valid in different contexts. Okay. But switching technology is expensive. It's expensive to learn something new. And in sort of the current modern day, we've got lots of new technologies that come up all the time. There's sort of something new every few months. If you want to switch to something new all the time, that'd be very expensive, particularly when our sort of data scientists don't have a lot of DevOps training. So we're in this sort of this high churn period. And that's expensive. That's frustrating. So we claim that future foundations to solve this problem within an ecosystem, like the scientific Python ecosystem, must be flexible, must be adaptable to other technologies. So Blaze, we're going to show, is a system that we are building that tries to leverage other systems and tries to connect users to other systems in a flexible, familiar way. So we're talking a lot about abstraction in three parts. We're going to talk about how Blaze expressions abstract over compute systems like SQL or like pandas or like Spark. Talk about how Blaze data descriptors abstract over data storage like JSON or CSV or HDF5. We're talking about how Datashape abstracts over data type systems. So we'll talk about all these things independently. I'll talk about the first one. Mark will talk about the second two. And again, we're sort of say that abstractions enable interactions, and interactions are good. Okay, so abstract computation. This is a little bit of Blaze code. Okay, so we've got a tiny data set here in the middle. Okay. And so we have a little tiny bank account. We've got lots of users, Alice and Bob. They have IDs, 1 and 2. And Alice, we owe Alice $100, and Bob owes us 200. Okay, so we might want to find all the deadbeats, all the names of the deadbeats. So I see that Bob and Edith, they owe us some money. So in sort of pandas-like code, we might say something like this: accounts of the balance is less than 0, sort of using NumPy-like indexing there, getting out the name. So this is sort of familiar to anyone who knows pandas. But I put this code at the top to show that it has nothing to do with the data. So this up here is a Blaze table symbol, and it's a totally symbolic, abstract representation of something we would want to compute. So there's no data behind that table symbol. It's just sort of something we can talk about. Okay. Then here at the bottom, we're going to combine it with some data, and then Blaze is going to cause some other machine to do some work. Okay. So we can swap out our Python data types with the data frame, and now Blaze is driving pandas. Okay. So, but the top code, the symbolic code, what sort of the data scientist might write down of what he wants to know about, that hasn't changed. Right? So we can swap between different data formats. And Blaze is driving the right computational engine to do the work. Okay, but it's not actually doing the work itself. Okay, so Blaze is not doing work. Pandas is doing work, because Pandas is really good at that, and we don't want to have to reinvent Pandas. So I'm going to give you a quick demo. Oh dear, there we go. So here's a quick demo. Is that text big enough? Someone in the back? Okay, right. Okay. So import from Blaze, we're going to get some error because something's wrong. This is Panda's fault. Pandas is great, but this one's Panda's fault. Anyone's used Pandas recently? That's not us. That's not us. Okay. So we're going to make our little symbolic table symbol. We're going to make some data. We can interact with that table symbol in a meaningful way. So like here's the columns that are in deadbeats. So you can actually do some error checking. It'll like yell at you if you do something wrong. If you care about symbolic expressions, this is the tree that's actually stored within deadbeats. So this is all just a fast Python object thing. It's all very simple. Well, we can compute against it. So we get out the names of Bob and Edith. We've seen this. We can load up into a data frame, and we get a data frame back. Right, so now we're just driving pandas again. We're not doing pandas work. We're just telling pandas what to do. And let's just spin up a little local Spark instance. So Spark is sort of like Hadoop, but it keeps things in memory. It's very nice for machine learning algorithms. It has an excellent Python interface. If there's one thing, just check out PySpark. It's actually a really nice project. But Blaze knows how to drive Spark. It's a bit more overhead, but this scales a lot more nicely. So if there's sort of one, selling point, oh, Blaze, it's like pandas on Spark. So that's something that you can drive. We can drive Spark pretty well. Let's load up a little SQLite database using SQL Alchemy. And we will generate some bad SQL, bad but usable, so this could be improved. But so now we're actually driving SQL to do the exact same computation inside of a small SQL database. Okay, so let's demonstrate some complexity. Let's say we know where everyone lives, okay, over where they might live. Okay, so person number 1 lives in New York City or in Boston. We can shove that data into a bunch of different data types. We can describe a computation. So we want to join our deadbeats table to the cities. We're joining on ID. We get the name and the city. Okay, so this is sort of where you want to send your collectors. This is where you want to send your goons. Okay, and so this is again a very symbolic thing. We can use this anywhere. So here we're going to compute in Python on pandas. We're going to generate a SQL expression, which we can also generate. Actually, just run that too, and we're going to use Spark. So we've done the exact same symbolic computation on lots of backends. So that's the idea behind Blaze. We're not at the moment trying to make a backend. We're trying to help data scientists leverage other backends that already exist. So you should be using all these technologies. They're all actually great technologies to use in isolation. If you don't need Blaze, don't use it. But if you want some help, if you want sort of a nice pandas familiar interface working with them, Blaze can help you with that. That's sort of lesson number 1. Okay, I'm going to pass off to Mark.
Thanks. Now, so we'll keep going through our other 2 abstractions. First, treating data uniformly. So just like with the computation projects that are out there, we have a lot of data projects. So CSV is really common. It's easy to understand. If you just open it in a text editor, you can see what's going on. JSON's popular on the web. HDF5 has a lot of scientific data in it. It's fast, binary format. It's good for storing multiple data sets hierarchically. We've also got distributed data sets. They've got different purposes. Each approach is valid in particular contexts, in particular situations. So we need all of them. We can't just say one format is the king of everything. And once again, to reiterate, spinning up new data formats, getting to learn about new ones is expensive. It can be frustrating to get your data in a format you've never seen before, have to deal with it. So let's take a look at CSV, same data that we had before. CSV here is a Blaze object. And what I'd like to point out is that when we do this, we're just probing the file. We're not loading it in NumPy and Pandas, typically, and many other systems. When you load a CSV, you load the whole thing. We're just kind of looking at the file and sort of mapping on top of it. So you can do some things already, look at the columns, get a little bit of information of what the data is. And then you can apply computations, indexing, all of the other things that we've seen before. But this is just grabbing a few rows, a few columns out of our CSV. And, well, if you got different data, a different data format, well, here's our HDF5 file. Just one little bit of extra information. You have to know which part of the HDF5 file you care about, and then it's exactly the same interface. So I go back, CSV, HDF5, it looks the same to the user. Same with SQL. So we've got a database, we connect to it. Once again, Blaze queries the SQL backend to get its metadata about the types, so it can understand and figure out what columns are there, and then we can run exactly the same code on all of these systems. So we're doing this with a data descriptor abstraction. Basically, there are two ways that we're working with it. One that's a little bit more interactive, user-friendly. So this is your standard Python iteration and indexing. And another which is chunked, and we want that because chunked is fast. We're able to take like data conversions or other things and do them a block at a time with fast code on each chunk. This enables that. But it's the same. So you have a CSV data descriptor. It's this API. And SQL, exactly the same API. So we have one API to target. These abstractions, they're uniform. Uniformity enables interaction. So here, kind of summarizing what we just saw, that with the same syntax, we're accessing all of these different data formats. It also enables interaction between different data formats, data migration. So you've got one system which wants its data in one format. It really needs to be in SQL, but all your data is in CSV. Having this uniform interface lets you easily transform or migrate your data. You don't have to become an expert in SQL and CSV parsers and everything. Same, like maybe you haven't seen HDF5 before, but someone gave you a data set in that, and you want to transfer it between SQL either way. All right, next topic, glue. So we've got these abstractions, compute, data. They're boundaries between these different abstractions or these different systems. So they describe their types differently. They have different names for things. They use different formats. One might store a date as a string. Another might store it as an integer. Another might store it as a different kind of integer. We need ways to map the types, and we need to be able to munge the data in between. There's lots of little details. So what we're doing, what we've created is Datashape is our data type system. It's array-based. and we can map it to many of these backends. So here's how it looks. It's very similar to the NumPy type system or many other type systems out there. So you've got your scalars, arrays. So this is 100 by 50 array of real numbers. And tables typically look like this. So you've got field names and types like strings, reals, dates. These are, oh God, we'll show you the example a bit later. But the other piece is, where do we collect all these little data adapters? What part of our system understands data in these little bit kinds of formats that everybody uses? That's inside of our project libdyned. So it's based on the datashape type system, so it understands datashape. It can store data in a very general form based on the datashape dimensions and types we've got. And it's got a lot of these understandings of binary and text formats. So it's like NumPy, but we've generalized it a little bit. I gave a talk last year introducing this project. It's evolved a lot. And we're using it, in this case, as storage and little bits of compute between all the pieces. So let's take a look at our demo. So we're first going to do look at an abstraction we built into Blaze for datashape discovery. So we've got a number 1. We can figure out it's an int. Arrays of ints. In this case, you see the second dimension isn't all the same size. We've got a var dimension for that. And kind of more and more complicated examples. But it's not just Python data. We understand data frames, SQL alchemy, and yeah, so you can see one type system that we're mapping lots of different backends to. I'll also take you through just a little peek at a slightly larger data set and data shape. So this is something collected from the Kiva project. So they publish their data set online in an archived format. We've taken that and combined it into one JSON file. Kiva, it's a micro-lending foundation that you can lend money to for really small loans, and lots of them in developing countries. So they're doing a lot of great work, and they publish their data. But this is in particular the loan data.
Optional values, or?
Yes, the question marks in data shape mean option float. That's right.
Not we're guessing it's floats.
Yes. So this data shape is fairly large, as you can see. And I'll point out, like down here in the payments, we've got a var dimension, so we're nesting variable dimensions because the number of payments for a given loan might vary. This is like contrasted with the NumPy strided fixed dimensions where you can't have it changing in the second dimensions. That's for sort of the more wild data ecosystem. This is an important thing to support. So if we now look at our file, this is a small subset of it, of the whole data set, 47 megs roughly. So Dyn lets you memory map it, so that's a bunch of bytes, and now we can parse it as JSON. So now X is a Dyn array that we've grabbed the JSON from, 10,000 records. And let's take a look at how we can slice and dice it a little bit with Dyn. Basically, the fields are accessible as attributes. So the names on the loans, we can slice it that way. We can, this one here. Loan amounts inside of the terms. So we're kind of, this is sort of that outer dimension, and we're just drilling down into our nested fields. But it's not always going to be like, you remember there was the var in there. So by going into settlement date, payments had a var array in there. So you can see up at the top, 9 payments, down below 3 payments. This is but quick access to various different ways. So this is a little bit messy. It's still a work in progress. Pretty formatting isn't quite there yet. But as a developer tool, it's great. We're using it to build out a lot of the sort of data munging in Blaze. So I'm going to hand it over to Matt a little bit, who'll show.
So I'm going to burn through this pretty quickly. But we just seen that internally, Blaze has lots of tools to deal with messy data across lots of different backends. We also care a lot about user interaction. So we've sort of shown lots of guts just to show that we can also appease users. We have sort of this interactive table object. You give it a piece of data, and it interacts with that data. Sort of like a pandas data frame. You actually notice we've actually just completely stealing the pandas printing mechanism. So here we're connecting to a Postgres database that's actually out another machine in our Austin office. Don't look at localhost. That's tunneling through the VPN. And we're generating queries over there. And we have this thing T, and we can just sort of play with T as we would a data frame, and it gives us back values that are sort of like what we expect. With another 0 in there. See what happens. So as I'm doing this, I'm actually touching a database remotely. And this database is the largest data set. This is Bitcoin. We can do split apply combine operations. Search happens very, very fast because we're only asking for 10 items that are on an index. So Postgres is nice. Uses at some point. This is actually generating out SQL, as we've seen before. But that's sending that SQL through the internet over to a database remotely, giving us back something back. We're pushing that into a data frame, presenting the data frame on the screen. It's sort of, we also have the tools to be pleasant. Here's a New York City data set, showing the first 10 lines, but this was the New York City released sort of unintentionally. All of their New York City cab data is all online. It's a fun data set. Here we're just getting 10 lines from a CSV file, but we could have sort of the sum of the same interactive usability for users. Okay, so let's finish and then stop for questions. Let's put up slides. Here's some thoughts. Questions?